When a set of equations are listed together, they are called a system of equations. These equations have solutions, just like algebraic equations. They may have one, none, or infinite solutions that can be found algebraically or graphically. To determine the solutions to a system of equations graphically, first graph each equation using its slope and y-intercept. Remember y equals mx plus b. Hopefully recall that m is the slope, while b is our y-intercept, meaning that's where it crosses the y-axis. Find where the equations intersect. This is the solution. Then state the solution and prove that it satisfies both equations. So let's take a look at question number 1. For number 1, we have two equations given. We're going to graph them on the coordinate plane, making sure that we label each equation to prove that we know which one is which, and then substitute the point that we find back into each equation to prove that it is a solution to each of the equations. So for number 1, taking a look at the first one, it's evident that the y-intercept is 6, so we go up to 6 and put our first dot. Then we count down 2 over 1 because the slope is -2. And draw our points for the rest of the line. Then take a straight edge and draw a line through the points. Arrows on both ends, labeling it with the equation. Next, we take a look at the second equation, which is y equals 1/2 x minus 4. So we start at -4. We count up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, or down 1 left 2, down 1 left 2, down 1 left 2. Draw your line through your points neatly with a straight edge. Yours should look much better than mine. And label it with the equation. And now we can see that the 2 points cross at the point where the 2 lines intersect, being +4, -2. From that, we can prove that that solution works in each equation. To prove that it works in each equation, we simply substitute it back into each equation. So 4 goes in for the x and y goes in for the -2. So plugging that back into the original equation, y equals -2x plus 6, we have -2 equals -2 times 4 plus 6, or -2 equals -8 plus 6. So we know -2 equals -2, so it works for that first one. And then we can also plug it into the second equation. So we have -2 equals 1/2 of 4 minus 4. So -2 equals 2 minus 4. So -2 equals -2. It works in both equations, so it is a solution for both of them, therefore a solution to the system of equations. Taking a look at number 2, we have y equals 3x minus 7. So we start at -7 on our y-axis. And we count up 3 and over 1. Up 3 and over 1. Up 3 and over 1. Then draw your line through the equation, through the points, arrows on both ends, labeling it with its function rule y equals 3x minus 7. Then looking at our second equation, we have y equals -2/3 x plus 4. So we start at +4, count down 2 over 3, down 2 over 3, or up to left 3, up to left 3. Draw your line through your points with your straight edge. Again, yours should look much better than mine. Label it with the function rule. Then circle the point where they intersect and label it with the coordinate. So in this case, the point where they cross is +3, +2. Now, remember, we also want to prove that that is the solution to both equations. So underneath, we're going to plug that into both. So starting with y equals 3x minus 7, we would do 2 equals 3 times 3 minus 7. So 2 equals 9 minus 7. So 2 equals 2, which is correct. Plugging it into the second equation, 2 equals -2/3 of 3 plus 4. Remember, 3 divided by 3 is 1, times -2 is -2 plus 4. And 2 then also equals 2. So we proved that it is a solution to both equations by plugging it back in, and therefore it is the point where they should cross on the coordinate plane, which we have already proven. You're going to now do the examples for the rest of the notes on your own. Make sure you're answering the questions on Go 4 Minute as you go.